Ever bumped into something, felt that weird pushback,
Hmm.
or maybe watched something like a spinning top just keep going and going.
Yeah, long after you've touched it.
Exactly.
Yeah.
Okay, let's dig into that feeling, that persistence. Because today, on the deep dive, we're really getting into the nitty-gritty of why stuff moves.
Or why it stays put.
Right. Why it stubbornly refuses to move.
Hmm.
We're talking the fundamental rules of how the physical world actually works.
Yeah, forget those dry textbook explanations. We've looked at the core concepts, the real-world examples, even, some of the numbers that pop up in physics.
So that's the plan.
Well, our mission today is to really pull out the essentials, the key ideas about motion and gravity, and how they're maybe surprisingly interconnected.
Okay.
And we want to do it without making your head spin. Think of it like unlocking the hidden rules of the game we all live in.
I like that. A backstage pass to the universe's choreography.
Uh-huh.
We're diving into Newton's 3 laws of motion and the law of gravitation.
That's the core of it.
So hopefully you'll have some aha moments. This is where we see how it all fits together. Let's start with the basics. Force. What is force, really, in simple terms?
Okay. Imagine you're trying to shove a heavy box, right?
Mm-hmm.
You push it, or maybe you pull it. That push or pull, that's a force.
Simple enough.
Yeah. Or a bit more technically, it's anything that can change an object's state, whether it's at rest or already moving.
Okay.
Or even change its size or shape, though. For today, we're mostly focused on the motion part.
Gotcha.
And we can basically split forces into 2 main groups. You've got contact forces where things actually touch.
Like your hand on the box.
Exactly. And then there are non-contact forces. These act over a distance like, a magnet pulling a paperclip towards it.
Okay, so contact force is the ones we kind of feel directly. Pushing, pulling.
Mm-hmm.
What else falls into that category?
Well, friction is a huge one. Think about sliding that box across the floor again.
Right, it doesn't just glide forever.
No, there's this resistance, right, between the box and the floor, trying to slow it down or stop it. That's friction.
Okay.
Then there's something called the normal reaction force. If the box is just sitting on the floor,
Mm-hmm.
it's pushing down because of its weight, obviously. But the floor isn't just collapsing, it's pushing back up with an equal force.
Ah, so that's the normal force.
That's the normal reaction force, yeah.
Yeah.
It stops the box from, falling through the floor. You feel it all the time. Like right now, sitting in your chair, the chair is pushing back up on you.
Makes sense.
Right.
Okay, what about things hanging or things crashing into each other?
Right. So if you hang, say, a picture frame from a wire, there's tension in that wire.
Okay.
The frame's weight pulls down and the tension the wire pulls up, keeping it balanced. That's a contact force.
Lens springs.
Springs, too. You stretch a spring, it pulls back, you compress it, it pushes out, it always tries to get back to its original shape.
Yeah.
That restoring force is how spring scales work, for weighing things.
Right, right.
And collisions, like if 2 billiard balls hit each other, during that tiny moment of impact, they each exert a force on the other.
Action reaction.
Exactly. We'll definitely circle back to that with Newton's 3rd law. It's a really key idea.
Okay, so those are the forces involving direct touch. What about the spooky action at a distance ones, the non-contact forces?
Yeah, these are often the ones that feel a bit more mysterious, maybe. The big one, the most obvious one, is gravity.
Can't escape that one.
Pretty much. It's that invisible pull between anything that has mass. It's why we're stuck to the Earth, why the moon orbits us, why, the classic apple falls from the tree.
And it depends on how massive things are.
Yes, mass is key. The more massive the objects, the stronger the pull. And also, distance matters. The closer they are, the stronger the force.
Mass and distance. Got it. Are there others besides gravity?
Oh, definitely. There's electrostatic force. That's the force between electric charges.
Like static electricity.
Exactly. Rub a balloon on your hair, stick it to the wall, that's electrostatic force at work. Opposite charges attract, like charges repel.
Okay.
And then there's magnetic force, the force between magnets or magnets in certain metals like iron.
Like a fridge magnet.
Perfect example. Or a compass needle swinging north, that's the Earth's magnetic field pulling on it. Another non-contact force.
So unlike gravity, which just seems to pull,
Always attractive, yeah.
these other can push or pull, and they get weaker the further away things are.
That's right. Electrostatic and magnetic forces can be attractive or repulsive. And yes, generally speaking, all these non-contact forces, including gravity, follow an inverse square law, meaning their strength stripes off really quickly as the distance increases.
Inverse square, meaning if you double the distance, the force is 4 times weaker.
Precisely. It fades fast. Think about Earth's gravity. It holds us down firmly, but astronauts just a few hundred miles up experience significantly less pull, hence weightlessness.
Fascinating stuff. Okay, before we get into how these forces actually, make things move, how do scientists measure force? What are the units?
Right. The standard unit, the one scientists use most, is called the Newton, symbol N.
The Newton, like Sir Isaac Newton.
Exactly like Sir Isaac Newton. 1 Newton is, roughly speaking, the force needed to, say, lift a small apple, or, more precisely, to accelerate a 1 kilogram mass by 1 meter per second squared.
Okay, and Newton.
There's an older unit, the dyne, from a different system, the CGS system. You might see it sometimes. But the Newton is the standard SI unit. For today, think newtons.
Newtons it is, the measure of push or pulse. Okay, now let's connect force to motion. Newton's first law, this is the inertia one, right? Things just keep doing what they're doing.
That's the core idea, yeah. Newton's first law, the law of inertia, it basically states that an object at rest will stay at rest. Unless acted upon by an external force, and an object in motion will stay in motion with the same speed and in the same direction.
Unless acted upon by an external force.
You got it. Now, that might sound almost trivially obvious to us today, but it was a massive conceptual leap back then.
How so?
Well, before Newton and Galileo, who did a lot of groundwork, the thinking was more like you needed a constant force just to keep something moving at a steady speed.
Oh, right. Because things here on Earth do slow down if you stop pushing them.
Exactly, because of friction and air resistance. But the first law strips that away and says the natural state is constant velocity, which includes being at rest, unless a force interferes.
So inertia is this, resistance to change.
Perfectly put. Inertia is that inherent property of all matter to resist changes in its state of motion. It's like the object's laziness or stubbornness about changing what it's doing.
And heavier things have more inertia, like trying to push a stalled car versus a bicycle.
Precisely. Inertia is directly proportional to mass. More mass means more inertia. Takes a much bigger force to get that car moving or to stop it once it is moving compared to the bike.
So is that why when a bus suddenly starts, you feel like you're thrown backwards?
That's inertia of rest. Your body was at rest, along with the bus. The bus gets forced forward, but your body, because of its inertia, kind of wants to stay put, lagging behind. That makes it feel like you're pushed back.
Okay.
We see it everywhere. Beating a dusty carpet. The carpet moves. The dust wants to stay put, so it falls off.
Right. Or yanking a tablecloth out from under dishes, if you're quick.
That's the trick. The dishes have inertia. They resist starting to move. Same principle.
Makes sense. And what about when things are already moving, inertia of motion?
Yep. If you're on that bus and it suddenly brakes hard...
You lurch forward.
Right. Your body wants to keep moving forward at the speed the bus was going. That's inertia of motion. That's why seatbelts are absolutely vital. They provide the force needed to overcome your inertia and slow you down with the vehicle.
Okay.
Or think about a cyclist who stops pedaling. They keep coasting for a while, right?
Mm-hmm.
That's inertia carrying them forward. Or an athlete doing a long jump, they run up fast to build up forward inertia, which helps carry them further through the air.
So the first law isn't just saying things stay put. It's defining force as the thing that changes the state of motion, overcoming that inertia.
Exactly. Force is the external cause that tends to change the state of rest or uniform motion. The first law tells us what happens when force is absent, which leads us naturally to
Newton's second law, which tells us what happens when force is present.
You got it. The second law quantifies the relationship.
Okay, this is the famous ESMA one, right?
Yeah.
Force equals mass times acceleration.
That's the most common form, yes. But there's a, let's say, slightly deeper layer involving something called momentum.
Momentum, okay, what's that?
Momentum is basically a measure of motion content. It depends on both an object's mass and its velocity. You calculate it as mass times velocity, so PP equals mv dollar.
Ah, so a heavy truck moving fast has way more momentum than a light bike moving fast.
Exactly, and it's harder to stop, right? That's related to its momentum.
Makes sense.
So Newton's second law, in its most fundamental form, actually talks about momentum. It says that the rate at which an object's momentum changes
The rate of change
is directly proportional to the net force applied to it. And crucially, the change in momentum happens in the direction of the applied force.
Okay, rate of change of momentum. How do we get from that to ICSE?
Well, think about rate of change. That means change over time, right? So $5 is proportional to delta P delta T then. Change in momentum divided by the time interval.
Right.
Now, if the mass of the object stays constant, which is true for most everyday things, unless you're like a rocket burning fuel,
Okay, constant mass.
then the change in momentum, delta to P, is just the mass times the change in velocity, the hours times delta V. So the law becomes $5 is proportional to mono delta V delta T.
And delta V delta T, that's acceleration.
Bingo. Change in velocity over time is acceleration. So $5 is proportional to mono dollars. And with the right choice of units, like the Newton, the proportionality becomes an equality.
Ah, I see. So Waml is like a really useful special case when mass isn't changing.
Precisely. But the momentum version, $5 delta T delta 2, is the more general statement of the law. It covers everything.
And this law gives us that quantitative definition of force, relating it to math and acceleration, things we can measure.
Exactly. It tells you how much force you need for a given mass and a desired acceleration. More force gives more acceleration. More mass means less acceleration for the same force.
And this also contains the first law, doesn't it?
It does. Think about it. If the net force $5 is 0, what does $5 tell you?
If F is 0 and mass isn't 0, then acceleration A must be 0.
Right, and 0 acceleration means
No change in velocity, stay at rest, or keep moving at constant velocity.
which is exactly Newton's first law. So the first law is just the second law applied to the specific case where there's no net force acting.
That ties it together nicely. Okay, real-world examples of the second law in action, besides just pushing things.
Oh, loads. Think about catching a baseball, a really fast one.
Ouch.
Right. If you hold your hand rigid, the ball stops very quickly. Small delta T dollars. The change in momentum is fixed, so if delta P dollar is small, the force, delta P delta T, must be huge. That's what stings your hand.
Ah, but if you pull your hand back as you catch it.
Exactly. You increase the time over which the ball's momentum changes. Same delta P path, bigger delta T means a smaller force for Forler, much gentler on the hand.
Clever. Same principle for airbags in cars.
Absolutely. And why high jumpers land on thick foam mats or pole vaulters in deep pits. It increases the time it takes to bring their momentum to 0, reducing the impact force.
And why dropping a glass on a carpet might be okay, but on concrete, smash.
Same reason. Carpet increases the stopping time, delta T tie. Concrete doesn't. Bigger force on concrete.
Really practical applications. Okay, that brings us to the third one, Newton's third law. Action-reaction.
To every action, there is always an equal and opposite reaction. That's the classic phrasing.
Sounds simple, but you mentioned a catch earlier.
The crucial point. The action force and the reaction force always act on different objects. They never act on the same object.
Ah, right, so they don't cancel each other out.
Exactly. If you push on a wall, action, your hand pushes wall, the wall pushes back on your hand, reaction, wall pushes hand. Equal forces, opposite directions, but one acts on the wall, the other acts on your hand.
Okay, so me pushing the wall doesn't cancel the wall pushing me?
Correct. Let's take walking. You push backward on the ground with your foot. That's the action.
In the reaction.
The ground pushes forward on your foot with an equal and opposite force. That reaction force is what actually propels you forward.
So the ground pushes me forward. Wow, okay.
It's this pair of forces in every interaction. A book resting on the table. The book's weight pushes down on the table, action. The table pushes up on the book with the normal force, reaction.
What about, say, a rocket launching? There's no ground to push against in space.
Good question. The rocket expels hot gas downwards at high speed. That's the action. Rocket pushes gas down.
So the reaction is?
The gas pushes the rocket upwards with an equal force. That's what lifts it off. It's pushing against its own exhaust gases.
Amazing. Like firing a gun, the bullet goes forward.
Action. Gun pushes bullet forward. Reaction. Bullet pushes gun backward. That's the recoil you feel.
So it's everywhere. Stepping out of a small boat onto a dock.
You push the boat backward, action. The boat pushes you forward onto the dock, reaction, which is why the boat drifts away.
Ah. Yes, I've done that. Okay, so 3 laws governing forces in motion. Now let's loop back to one specific force. Gravity. Newton's law of universal gravitation.
Right. This is the big one for understanding orbits, falling objects, the structure of the universe, really.
So what does it state?
It states that every particle of matter in the universe attracts every other particle with a force. And this force is directly proportional to the product of their masses.
Meaning more mass, more force.
Yes. And inversely proportional to the square of the distance between their centers.
The inverse square law again.
Yeah.
Further apart, much weaker force.
Exactly. The equation is $1 is g m1 Miller 2 r22, where $m and tidal 2 are the masses, trawlers is the distance between them, and dollars is...
The universal gravitational constant. What is that?
G is just a fundamental constant number. It sets the actual strength of gravity. It's the same value everywhere in the universe, as far as we know, and it's actually a very small number.
Which is why we don't feel pulled towards, say, a filing cabinet.
Precisely. The masses of everyday objects are too small for the gravitational force between them to be noticeable. You need something with enormous mass, like a planet or a star, for gravity to become a really significant force.
But it is acting between me and the filing cabinet, just incredibly weakly.
Technically, yes, but utterly negligible compared to the Earth's pull on you.
And gravity is always attractive.
As far as we understand it, within this framework, yes. Always pulls things together. It's the architect of the cosmos, holding planets, stars, and galaxies together.
And this law explains why things fall down.
It does. The Earth is a huge mass. You have mass, so there's an attractive force between you and the Earth. We call that force your weight. It pulls you towards the Earth center.
Okay, weight is the force of gravity on me. What about G, the acceleration due to gravity? How's that related?
Good connection. So, if the only force acting on you is gravity, like if you jump off a diving board ignoring air resistance for a moment, you're in free fall.
Right.
And you accelerate downwards. That acceleration is G. Galileo famously showed, or at least, story goes, dropped things off Pisa, that all objects accelerate at the same rate G in free fall, regardless of their mass.
So a feather and a hammer fall at the same rate in a vacuum.
Exactly. We can even calculate G using Newton's law. The force on you is your weight. ME dollars. It's also given by the universal law, GMRM R22, where M is Earth's mass and R is Earth's radius.
So my mass cancels out.
It does. You're left with GMR222. The acceleration due to gravity only depends on the planet's mass and radius, not the object's mass.
Which is why G is about 9.8 meters per second squared here on Earth.
On average, yes. It varies slightly depending on altitude and latitude.
And on the moon, where M and R are different, G is much smaller.
Right, about 1/6 of Earth's G. That's why astronauts could bounce around so easily.
So in free fall near Earth, your speed increases by about 9.8 meters per second. Every second.
That's what acceleration means, yes. Ignoring air resistance, of course.
Okay, and just to be super clear, let's nail down the difference between mass and weight one last time.
Absolutely essential distinction. Mass is the amount of stuff, the quantity of matter in an object. It's measured in kilograms. It's an intrinsic property. Your mass is the same whether you're on Earth, the moon, or deep space.
Mass is constant, okay.
Weight, however, is the force of gravity acting on that mass. Since it's a force, it's measured in newtons. And because gravity varies, GI Galileoways is GMR222, your weight changes depending on where you are.
So I weigh less on the moon because the moon's G is less, but my mass hasn't changed.
You've got it. Mass is the measure of inertia. Weight is the gravitational force. We often use scales that measure force but display it in mass units, like kg or pounds, assuming Earth's gravity, which adds to the confusion sometimes.
That clears it up. Wow. We've gone from basic pushes and pulls through Newton's 3 laws explaining how things move under forces, right up to the universal force of gravity shaping the cosmos.
It's quite a journey, isn't it? And amazing how these few relatively simple laws underpin so much of our understanding of the physical world. They really show how interconnected everything is.
Absolutely. So as you go about your day, maybe think about these laws.
Yeah.
Standing still, walking, driving, even just watching something fall. It's all governed by these principles.
That interplay of forces, inertia, mass, acceleration, gravity.
Yeah. Here's a thought to leave you with. We talked about gravity being universal, acting between all matter. Yeah. What might be some of the less obvious, maybe more subtle consequences of this force being absolutely everywhere, acting on everything all the time? Something to ponder.
A good question for sure.
Well, thanks for joining us for this deep dive into the fundamentals of motion and gravity. There's always more to explore.